Hi everyone, this is Jonathan of the Gift of Maths. In this video, I'll be talking about how to randomly calculate areas and integrals. Now, this is my first video, so I'm going to say something quick about myself. I have a PhD from the University of Cambridge. I work now mainly in mathematics education, but I still do research at the University of Hong Kong. Okay, so that's enough about me. Let's get started. Let's start all the way from the beginning. When you first learn about area, you learn about the area of basic shapes, such as these shown here. The next step after that is to look at compound shapes. Shapes made up of the basic shapes, such as this one over here, made up of a semicircle, a rectangle, and a triangle. Get the area of each part, add them together, you have the area of this shape. But what about stranger shapes, like this mysterious shape we have over here? If we want the area, we probably can't find the exact area because this shape is not made up of the basic shapes. What we can ask for is an approximation. To get an approximation of the area, the standard way is to put it on a grid, like we did over here, and then start counting the squares that are inside the shape, and then all we have to do is add up the area of these squares, and we have an approximation for the area of this mysterious shape. If you want a better approximation, all you have to do is take a finer grid, smaller squares, add up the number of squares that are contained inside the shape, and then you get a better approximation. Now, we're not going to be talking about this kind of approximation of area. We're going to look at a different way to approximate the area, and this way uses probability. Let's start by looking at a problem. You've probably seen something similar before. A dart is thrown at a target, and the target is some sort of shape drawn on it. So here the target is the square, and the shape you want to hit is the red triangle. We assume the target square is always hit, and the question is, what is the probability that we will hit the red triangle? Now, you probably know that this type of problem is solved using the idea of geometric probability. So the probability of hitting the shape, the red triangle, that's the area of the shape divided by the total area of the target. Now, another thing about probability that you know is, for example, the probability of hitting the shape is 1/2. Then that doesn't mean that every 2 throws will hit the shape once. It's sort of a long-term proportion type of thing. So in other words, we imagine that we throw a large number, let's say 1,000 darts at the target, then the proportion of times you hit, that should be approximately equal to the actual probability of hitting the shape. Now, combining these two formula, we have this thing over here. Now, this is the key formula that we're going to use. We just do a little rearrangement, and we have this thing over here. So the area of the shape, remember, that's the thing we're trying to estimate. That's approximately equal to the proportion of times the shape is hit times the total area of the target. Now, obviously, I'm not going to be throwing darts at anything. So what we're going to do is we're going to use a computer to simulate this. Okay, so here's a simulation I put together very quickly just using Scratch. We have the white square, which is the target, and the green circle, which is the shape we're trying to hit. Now, let's say the circle has a radius of 1, so the square will have a side length of 2. The area of the square is 2 times 2, which is 4, and the area of the circle using pi r squared will just be pi. So we're going to throw around 200 darts at the shape. Not all of them will hit, so we're just going to count the ones that hit. And then we're also going to count the ones that land inside the green circle, hence giving us an estimate of the probability using the geometric probability formula we had previously, and hence, using the formula, we're going to get an estimate for the area. So let's give that a go. Okay, total is going up, inside is also going up. Let's see, so in the end we have 117 darts that land inside the target square, of which 97 hit the green circle. So that gives an estimate of the probability, which is 0.83 around, and the area, which we got to be 3.3. So we know that, of course, pi is approximately 3.14, so we don't really have an accurate result. We have it to essentially one digit, one significant place. If I run this experiment again, I'm going to get different results, but usually, most of the time, we will get one significant figure of accuracy. We'll get the 3. Now, we want to do it more times, but we actually don't need to visualize anything. So I'm going to use a spreadsheet right now to simulate it more times. A lot of numbers here, but don't worry. The first 2 columns are just randomly generated x and y coordinates that are inside the square. Then for each of these coordinates, we ask, is it inside the green circle? And if it is, we put yes, and if it's not, we put no into column C. Then we did this 3,000 times, so we have 3,000 coordinates here. We have 2,359 that are inside the square, we get an estimate for the probability and an estimate of the area, which is 3.145. So that's 3.15 to 2 decimal places. Again, we know the true area is 3.1415 and so on. That gives a percentage error of 0.37. So we've done a little bit better here than before. We now have 2 significant figures of accuracy, 3.1 essentially. I can do this again if I generate new numbers. Of course, the estimated area will be different. You can actually do the same thing for volume as well. Now here, I have a sphere inside a cube. I generate 2 random coordinates, x, y, and z, and I ask, are we inside the sphere? So we did this 3,000 times as well. We have the number inside is 1,586. That gives an estimated volume of 4.22. To get the true volume of a sphere, we do 4/3 pi r cubed, which is 4.1887. Now, that gives a percentage error of 0.96%. So we can see that it's still not very accurate, but the key thing here is that the accuracy we got for the sphere is very similar to the accuracy we got for the circle. Let's think about what we have so far. So we estimated area using probability, using randomly chosen coordinate points. We extended that to volume by using randomly chosen 3D coordinate points. We saw, okay, well, kind of works, but they're both similarly not that accurate. Okay, we had a similar error for both area and for volume. Now, what's the point of this? Area, volume, yeah, maybe that's not that interesting, but one of the key things is we know that integration corresponds to finding areas. Here we have the integral from a to b of f of x dx. For example, the integral from 0 to 1 of x squared e to the minus x, the graph of which you can see over here. We know that the integral represents the area under the graph, and we now know we can estimate areas using probabilities. As you move on with your calculus education, you'll learn about multiple integrals such as this one over here. This essentially represents a volume, and we also know that volume can be estimated using probability. You'll learn that integration, you can repeat it as many times as you want, such as this guy over here, which corresponds to some 5-dimensional equivalent of volume. So we don't really need to worry about what that is. We just need to know that this integral over here can also be estimated using probability. So multi-dimensional integrals can be estimated using probability. We saw in the area case that if we take more points, then we get a more and more accurate answer. And we've also seen that for area and volume, taking the same number of points, we get a similar error. This over here, that's the key observation. Because no matter how many dimensions, the error will be pretty much the same. In other words, the error doesn't depend on the number of dimensions. If we take more and more points, no matter what dimension, we'll get a more and more accurate answer. Now these functions of 5, 6, however many variables, they don't have to be spatial variables. We live in a 3-dimensional space. If you include time, then it's a 4-dimensional space. These multivariable functions, they occur in many fields. For example, in economics, if we have the quantity demanded of some item, that depends on its price. It also depends on the price of competitors, complementary goods, that sort of thing. So in these cases, we may want to do an integral like that, and that integral can be estimated using probability. No matter how many dimensions, we'll get a similar error, so all we have to do is take more and more points. This method of using probability to estimate the value of an integral is called Monte Carlo integration. Monte Carlo, the city in Monaco famed for its casino, its main advantage is that its error doesn't depend on dimension. No matter what dimension the integral is, the error will be the same. Other methods of estimating the value of integral that you might know, the trapezium rule, that error is strongly tied to the dimension. If we have too many dimensions, essentially the rule is too slow to be used. This is where Monte Carlo integration has its advantage. So thank you for watching my video. Apologies for the lack of production quality, but I really do hope to continue these videos on math topics that interest me. Thank you once again. Have a good day.